start with an event and an observer. Event and observer. Event is something that is what is happening. One second, this is the event and observer. Event is something what you observe. Just write down. In the meantime, I will adjust my slate. If any person who is in a laboratory frame, any person who is in the laboratory frame is observing an event, then he is said to be in a frame. He is said to be in a frame which is at rest. He is said to be in a frame which is at rest. And such an observer is called, a stationary or inertial observer. Such observer is called an inertial observer. One second, I am just getting back. So therefore, to describe such an event, you require what is known as a Cartesian coordinate system. You require what is known as a Cartesian coordinate system involving x, y, z and t. Involving x, y, z and t. Involving x, y, z and t. And x, y, z, as you know, are called spatial coordinates. X, y, z. X, y, z are called spatial coordinates, and t is small t. Small t is a time coordinate. It is a time coordinate. Suppose you have another event. In which you are observing it, another event which you are observing from a frame which is moving, from another frame which is moving, then you need different frame of reference. Then you need a different frame of reference. You need a different frame of reference. And to describe that, you need different set of coordinate system. You need a different coordinate system, and this coordinate system is completely different, and this coordinate system is completely different from the previous one. It is completely different from the previous one. To describe an event, let us see, to describe an event, you do not require, you do not require any, what you don't require to describe it? It doesn't require any frame of reference. Event can happen anytime. Okay, I now got my bag. Okay. So now, to describe an event, it does not require any frame of reference. It doesn't require any frame of reference. For example, say suppose you are observing the rocket launch. This rocket launching is an event. You can watch it from your TV channel. So this is one frame of reference. You can watch it from the control room. The scientists only have the access. We cannot go there. So from the control room where this mission is going, this is another frame of reference. Then you can also, where else can you watch? You can also watch, let us say, that from another planet. Suppose you are watching it from another planet. This is yet another frame of reference. So what is the event here? Event is launch of a missile or a rocket. What is a frame of reference? The frame of reference can be, it can be either your TV frame or your control room, or it can be from another planet. Isn't it? Therefore, that means you have here different options. You can watch the event from any frame of reference. You can watch it from any frame of reference. Okay. So in view of this, let us try to understand something called as, let us say, some transformations are required. Therefore, you require some transformations. You require what is known as, let me show you. You require therefore the transformations. They are known as Galilean Transformations. They are referred to as Galilean Transformations. What are these Galilean Transformations? They are used to observe an event. They are used to observe an event. So let us consider two frames of reference. Let us consider two frames of reference described by S and S prime. S prime is a moving frame and S is a rest frame, or also known as a laboratory frame of reference. So now draw two Cartesian coordinate systems, all of you. All of you draw two Cartesian coordinate systems in such a way that x-axis coincides. Draw it in such a way that x-axis coincides. Maybe I'll draw it, that would be better. This is my x-axis. This is my y-axis. This is my z-axis. So now call this as x dash, this is y dash, this is z dash, and this frame you call it as S prime frame. Okay, the other frame, for this frame, this is my x, this is my y, this is my z. This frame, let us call this as S. Let us try to describe an event which is given by, let us say, some position P. Okay, some position P whose coordinates are x, y, z, t in S frame, x prime, y prime, z prime, t prime in S prime frame. We'll just wait, just draw it and keep it. Let us say that the frame S prime is moving, let us say, with a velocity v. We said it is a moving frame, so let v be the velocity of this moving frame. Which frame? We are calling it as S prime frame. So when this is the velocity with which this frame is moving, let us describe the position P with respect to, let us say that this position is here, this position is here. So what is this distance? This distance, let us say that it is moving with the velocity S prime along x-axis. Let us say that it is moving only along the x-axis. Only one frame at a time we will consider. We will try the other things later. That means, so there is a small point here. That means there is no change. That means there is no change along y and z axis. It's moving only along the x direction. Fine. Then, if this is your x dash, it is moving with what velocity? It is moving with the velocity v. Okay. Initially, this event, what is the event? Let us say you are flashing a torchlight. Flashing a torchlight, simple event. This is your event. This event is happening at a position of x, y, z, t as observed by as observed in S frame. It is observed as x dash, y dash, z dash, t dash. In which frame? As it is observed in S prime frame. Very important observation here, that at time t is equal to t dash is equal to 0. This is start of the event. This is the start of the event. Both S and S dash start from the origin. They are coincident. The origins do coincide at time t is equal to 0. Okay, fine. So far so good. After a time interval, okay, after a time interval, let us say that after t seconds, what is happening at t seconds? Which frame is moving? S prime frame is moving. When S prime frame is moving, this is my S prime frame. It is now moving. At what distance it's moving? What is the distance covered? S prime is moving to the right, isn't it? So, when you are observing, one more important observation here. What was the distance we said? This distance is, what is this distance? This is x. This distance is x. Okay. Now, what is the distance of this with respect to this? That distance is, which distance is, this is the point. So, let me draw. This is the point, right? So, this is x prime. Now, initially both were at this origin, if you remember, at time t is equal to t dash is equal to 0. Now after t seconds, this has moved this distance. How much distance it has moved? What is the distance that it has moved? This much distance has been moved. What is that distance? You already know that distance by time is your speed. It is moving with what speed? V. In what time? T seconds. So how much distance is it moving? V into T. So that means this distance what we are talking about is nothing but V into T. After T seconds, the frame S prime is moving by a distance which is equal to Vt. Therefore, can I write from this figure, x dash only is this distance. The total distance is x. What is x dash is equal to? Can someone prompt me from the figure? From the figure, okay. From the figure we can write. Girls, am I audible? Are you all able to follow me? One of you please give me a feedback. X dash is equal to x minus Vt. I just want a feedback. Are you able to follow? One of you please.
Yes, ma'am.
Okay, fine. Fine. Thank you. Then, as we said, there is no change along y and z directions. Because there is no change, we will write y dash is equal to y and z dash is equal to z. These equations are known as Galilean transformation. Galilean transformations. They are called Galilean transformations. And what is very important here is that Newton's laws of motion, Newton's laws of motion could not change Galilean transformations. It could not change the Galilean transformations. So, anything which does not change, the one which doesn't change is called as a constant, which you all know, or we can also say that that is something which is invariant. Invariant is one which doesn't vary or one which remains constant. What is important now here is, as long as frames are not moving, as long as the frames are not moving, these Galilean transformations are useful. These are useful. But when the transformations, when the frame is moving, as is the case in this present case, they will not give correct results. They will not be able to give you the correct results. So, let us write when space coordinates are given by these equations, number 1 given below. Let us see now how velocity and acceleration are changing. Let us see how velocity and acceleration change under Galilean transformations. So, since we have from the equation 1, we have x dash was equal to x minus vt. So, differentiating equation 1, this was equation 1, with respect to t, what do you get? You get dx dash by dt is equal to dx by dt minus v. Why v is not taken into derivative? Since it is moving with a constant velocity, so v was constant and hence it is taken out of differential. So let us write this as velocity. This is nothing but velocity. Let us write this as ux dash is equal to ux minus v. Equation number 2. And what will be dy by dt? Next equations are since y dashed was equal to y dashed was equal to y and z dashed was equal to z. So that means dy dash by dt is equal to dy by dt and hence dz dash is equal to z. So what do you write from this? You can write, what do you write? Y dash is equal to y and I'm sorry, not y dashed, uz dashed. This is velocity, right? So, what do we write? U y dashed is equal to uy, u z dashed is equal to z. So, what do you conclude from this? We conclude that u dashed is equal to ux dashed is equal to ux minus v, uy dashed is equal to uy, uz dashed is equal to z. So in other words, since only one parameter is changing, it is simple to write u is equal to u minus v. So finally, what you have, very important relation, that u dashed is equal to u minus v. Fine. Now, let us try to get the components for acceleration. To get a component for the acceleration, you differentiate this. If you call this as x component, you can see it's only one. Whether you write x or you don't write, it doesn't matter. So now differentiate equation number 3. What do you get? You get dux dashed by dt is equal to dux by dt minus dv by dt. Now what do you observe? You have here a component dv by dt. What is dv by dt? Time rate of change of velocity, where v is constant and hence it is 0. So therefore you can write, what do you write? This is nothing but ax dash is equal to a. Ax dash is equal to a. So Ax dash is equal to A. This is the equation. What we get similarly, Ay dash. So Ax dash is along x. Ay. Similarly, Az dash is equal to Az. Therefore, we can write in short A dash is equal to A. Multiply both sides with m, you get ma dash is equal to ma. It implies, what does it imply? Force in primed frame F is equal to that in unprimed frame or stationary frame. So very important conclusion. What is the important conclusion that we are writing here is the acceleration, very important, the acceleration is the same, acceleration is the same in both S and S prime frame. S as well as S prime frame. When acceleration is same, it implies force also is same. So what do you conclude from this? That acceleration, very important thing is acceleration and force are invariant. They are invariant in Galilean, what transformations? These are Galilean transformations. So these Galilean transformations are defined in what physics? Known as classical physics or classical mechanics. We will study quantum mechanics when you come to final year. So as long as classical physics or classical mechanics is concerned, the acceleration and force are invariant. That means they remain the same. They remain the same. Okay, so far so good about these transformation equations that we are talking about. Okay, so now let us see something more than this. So let us now talk about, I don't know whether is it clear enough for you able to see. Okay. So now let us take the existence of ether. Let us talk something about existence of ether as a medium for propagation, of light. This is a very, very important consideration as far as the classical mechanics is concerned. Let us see what we are talking about. Initially, in the 19th century, we are in 21st century now, we are talking about 19th century. The physics started there. In that year, in the 19th century, the scientists thought that a medium is required for the propagation of light. They thought a medium is required for propagation of light. They know that sound requires medium. As sound requires medium, they thought light also requires medium. And for the measurement of this sound, to measure velocity of sound, when you know there is something existing and it is moving, this medium is moving. So in physics, we cannot just state any statement. We have to prove it, we have to define it, and we should be able to measure it. Then only that particular quantity has a relevance and also has a meaning. Therefore, they measured the velocity of sound with respect to air. They measured the velocity of sound with respect to air as the medium. That means what they measured is a relative velocity of sound with respect to air. Relative velocity of sound with respect to air. And also, because by then, since Galilean transformations were already known, they even tried to apply these Galilean transformations. So what else is required? We also require what is known as an inertial frame, the one which doesn't change, inertial frame of reference. All these were required. If there was a medium like that for light, if they can think of a medium for the light, and initially they thought either is a substance which was a medium, which was present all over, and light is passing through ether, is what they thought. Light is passing through this ether medium. Scientists are the ones who carry out experiment. They determine something, they make a measurement, and they compare it with the standard values. If they are correct, then they say whatever experiment they have done is correct. Okay? So suppose you are doing simple pendulum experiment. You calculate, you take a length, you take time period, and you calculate the velocity of acceleration due to gravity using, what do you use? G is equal to 4 pi square L by T square. You change length, you get different time periods. You carry out this experiment number of times, tabulate the results. You carry out this experiment, you tabulate your results or your observations and calculate G value find the average G value, and it should be close to 980 centimeter per second square. If you are getting very large value or very low value, your lecturers will ask you to repeat. It is not satisfactory. Likewise, they conducted many experiments to prove the existence of ether. So, many experiments have been carried out to prove the presence of ether. To prove the presence of ether. So, what was the experiment? The experiment was carried out by two scientists, namely Michelson and Morley. These two scientists have carried out an experiment in which year, I think in the year 1881. In the year 1881. We are calling it as 19th century. So before I talk, first draw the circuit, then I will give you the explanation. Draw it along with me. I will give you the description. First, draw the circuit along with me. These two, and then one more here. It should be at the same level. Try to draw it at the same level. This is the source S. This is the source of light. It is traveling in this direction. This is the source of light. It is traveling to the right. And Earth's rotation is from south, north, west to, this is how it's moving. So it's moving from in this direction, isn't it? So that means we said there is ether. This is ether, medium. It's moving with a velocity v. if you have copied. Let us imagine, write down the points. S is a monochromatic light. This is a monochromatic light. Is falling on a mirror here. This mirror is half silvered mirror. This is a half silvered mirror. So this light, when it is falling on this, part of it is transmitted, a part is reflected. So this is reflected beam of light. This is transmitted beam of light. This is making an angle of, as you can see, 45 degrees with the incident light. It's making an angle of 45 degrees with the incident light. So it is splitting into two beams. What is happening? The incident light, first point, incident light is split into two parts. What are the two parts? Reflected beam and transmitted beam. So this is the experimental setup. The experimental setup is like this, and they fixed two mirrors, M1 and M2, at right angles to each other. M1 and M2 are fixed at right angles to each other. So what's happening? This transmitted beam, after reaching this mirror here, gets reflected in this direction. Similarly, imagine now Earth is moving. This is stationary, there is no problem because it's in the same direction. In the same direction in which light is moving. Okay, either is moving in this direction, no problem. So what is happening? It is moving with this velocity. The velocity of light is denoted by the letter C. So if it is moving in the same direction, it is C plus V. In this direction, it is C plus V is the speed. In the other direction, opposite direction, it is C minus V, relative velocity. So far so good. Another interesting thing what happens here is, let me take this. This light is a reflected beam. It is trying to reach this mirror M2. This is again partially silver. So this light is expected to be reflected back. Now one interesting thing what happens here is, since the entire medium is moving like this, this light, this is like a river. This is the opposite bank. And a boat is moving. This boat is moving, trying to reach this point here. But river is also flowing. So it is as though river is like your ether medium. It is trying to reach this point. Let us say this point is B. But by the time it starts from here, by the time it reaches, this point is no longer here. It would have moved to B dash. That means what is the path it is taking? The light ray? The light ray is taking this path. And this velocity is v. Isn't it? This is a light, it should have gone to B, but by the time it goes, it is reaching the point B dashed with a velocity c. But why is it happening? Because either is moving, it is moving in this direction, either is moving in this direction. It is moving from B dash to B with a velocity equal to v. And this is a right angle triangle. So what is happening? This beam which was reflected back will be moving with what velocity? C square minus v square under root. What am I applying? I am applying a Pythagoras theorem. C being greater than v, c square minus v square is the velocity with which the light is reflected back. Therefore, what is interesting here now is that let this distance of this mirror is d, and this distance also is d. They we both placed at the same distance. Maybe you can take a screenshot of this entire figure. I will try to post the material as well as this lecture, but in the meantime you copy. So what happens? These two both are reflected. The reflected beam is reflected back. You can see the arrow here. The transmitted beam is also getting reflected. It undergoes further transmission, and these two will undergo what is known as interference. And when you watch it through a telescope here, you will be able to, this is a telescope here, you will be able to see interference pattern. You will be able to see interference pattern. These two undergo interference. And that interference pattern is alternate light and dark lines. I'll tell you what these lines are. This is what you see. So therefore, let us consider two beams now. What are the two beams that we consider? First, transmitted beam. Let us consider a transmitted beam. So, initially, what is happening is from the mirror, center mirror, to go to M1, let us call this time as T2, T by C minus V. Isn't it? The distance is along the direction, relative velocity. Then, when it is moving from M1 back to M, let's call this as T2 double dash, that is D by C plus V. Distance by time is velocity, distance by velocity is time. So let's call this as equation 1, equation 2. Therefore, the total time T2 is equal to T2 dash plus T double. Total time, no, it's going from one mirror to the right. It's going to the right, coming back. So T by this total time. The total time therefore will be given by, what will it be given by? D by C minus V plus D by C plus V, which can be defined, which can be simplified as C square minus V square is common. So you get it as c square v square, which can be written also as 2d by c 1 minus v square by c square. There is something for this equation. We will tell you what it is. It has a significance. Similarly, for the reflected beam, reflected beam is going to top and coming back, isn't it? What is the reflected beam? It's going here and coming back. So what is the time it is taking? Let us see. Let's call that as T1. So what is the time it is taking? The velocity is c square minus v square. So it is traveling a distance of d. It's coming back by a distance of d. Therefore, the total time, what will be the total time? Let's call this as t1. It is not different as is the case here. It is the same. Total distance is 2d by c square minus v square under root. Isn't it? Which can be written as 2d by c into 1 minus v square by c square to the power minus half. How am I getting this? I will take c. This is 2d by c common. So 1 minus v square by c square under root. So which can be nothing but equal to 2d by c can be taken out. 1 minus v square by c square to the power half, plus half here. So when you take it to the numerator, you get it as minus half. Let me just complete this. It's 12 o'clock, but I'll just complete this. So by using your binomial expansion, this can be written as 2d by c into, it's in which form? 1 plus x to the power n. So it is 1 plus nx plus nx square and so on. Since the velocity of light is very much greater than v, we consider only the first term. It's in the denominator. C is in the denominator. C is very high compared to velocity. So this factor is very small. If a term in the denominator is very high, the fraction is very small. So we consider only the first term, neglecting all the higher order terms. So it is 1 plus nx. So 1, okay, this is minus, right? 1 minus half. So 1 minus half into minus. So it is 1 plus half into v square by c square. So both times you have, so there is a time difference. Therefore T2 can be written as this. So that means the time difference between these two can be written as T2 minus T1 or T1 minus T2. So in short, we write this as T1 difference T2. It means either which can be more, which can be less is immaterial here. So the difference in the time between the two intervals T2 minus T1 can be written as 2d by c. I am just copying those expressions here. 1 plus v square by c square minus this above equation 2d by c into 1 plus v square by 2c square. If you simplify this, what you get is 2d by c minus 2d by c get cancelled, isn't it? And then now you have 2d v square by c cube minus 2d v square by 2c cube. So this is reduced to d v square by c cube. If this is the time difference, then the path it travels will be given by c into delta t. Time into velocity of light. That will be equal to dv square by delta t. So c into delta t. So d v square, this is c cube. So dv square by c square. This path is nothing but called as the wavelength. This is called as wavelength. I think you know what a wavelength is. So if you take something like this is one time period, our distance is 1 lambda, the wavelength. So we can write path difference. So therefore d v square by lambda c square is your path difference. Just make a note, just one more minute. If the apparatus is rotated by 90 degrees, if the apparatus is rotated by 90 degrees, so whatever fringes you are getting, you are rotating it by 90 degrees. So you have some fringes here like this. Then you rotate it by 90 degrees, okay? Then you have different set of fringes. Rotate it by another 90 degrees, you have different set of fringes. These fringes shift. I will stop here. I will continue in my next class. So what we are talking about is the difference in the fringe shift and what happens, what they thought initially, they estimated there is a shift. See, when you disturb the apparatus, the entire thing is disturbed. When it is disturbed, there was a change. So when there is a change, they thought something different will happen, and they thought that